you enjoyed your week? I hope you enjoyed your weekend and have made some headway through the first problem set as we'll sort of move into the more mathematical part of thermodynamics. So there's some readings I would recommend at this point. Callan, we're kind of making it through chapter 2. You know, we don't cover things exactly the same way as Callan, but I would recommend you read through 2.1 and 2.8 and 3.1 to 3.3 and 4.6 and 4.7. De Fontaine describes what I'm doing in this lecture and next fairly briefly, but it's kind of covered in chapter 3 and 4, except that in chapter 3 he sort of starts with the zeroth law, and I haven't really spent any time on that, so you can skip that if you want to, or you can read it out of interest. He also has a somewhat different statement or a somewhat different argument to build up the second law. So good. So let me recap where we were. Okay. So we joined the first and the second law, right? In writing a fundamental differential. And again, it was the first law who told us that this piece that comes from heat flow, TdS, and the part that comes from work on the system is equivalent in terms of energy content. But then it was the second law that told us they were actually different, right? The second law told us that the energy you're bringing in by doing work is really different from the energy that you're bringing in by doing heat. And in some way, right, the second law is a quantification of that. You could think of entropy as the measure of the heat you brought in, but with the normalizer of T, right? So it's really sort of T times the entropy change that's equal to the heat you brought in. But in some way, entropy is a measure of the heat you've brought in, right? Later in statistical mechanics, we'll see that these are indeed fundamentally different ways of changing the energy. We'll see in statistical mechanics that work will be changing of the microscopic energy levels, right? And a macroscopic system fluctuates between different states, and work will be fundamentally changing the energy of the states. Heat will actually simply be changing the distribution of the states. So if you pump the distribution across the states. So if you pump energy as heat into a system, you're not modifying the energy levels, but you're going to modify how much it sits in higher energy levels versus lower energy levels. And more heat will mean that you occupy relatively more energy levels. And if you think about it, it's sort of remarkable that classical thermodynamics got to this point, right? That they basically uncovered something that maps exactly onto what we'll later learn from microscopic descriptions of matter, but without actually knowing anything about it, right? Thermodynamics was defined and developed well before we even knew there were atoms in materials. And it's kind of remarkable that, you know, as we'll see later, this maps exactly on two fundamental differences in microscopic statistical mechanics. So you can develop the fundamental equations of state from this, right? We now know that the intensive variables are derivative of the potential with respect to the extensive conjugate. And I gave you as an alternative the entropy formalism. So this is the energy formalism. I could write the entropy formalism, which I'll occasionally use in thermodynamics, but which we'll use a lot more in statistical mechanics, which is simply a rewriting of this. and in which you get fundamental equations or equations of state that are slightly different as well. 1 over t is ds du at constant xi, and minus y over t is the derivative of the entropy with respect to the extensive variables. Okay. The last thing we learned is that this once and for all figure closes out the confusion about variables in systems, right? So if you're going to analyze a thermodynamic system, you want to figure out how many ways it can receive energy from your environment, right? That's the number of work terms. Assuming you're at constant temperature, that's always one heat flow you have, one energy flow you have. But you'll figure out how many work terms there are, and if there are n work terms, right, then there are 2 times n plus 1 variables. And if you remember, there are n plus 1 equations of state. So that means your system has n plus 1 degrees of freedom. So if I work with an electrically charged system, let's say a capacitor, or in materials that could be an interface, right? An interface does not have to be charge neutral. A bulk material has to be an interface, doesn't have to be because it's finite in thickness. To do thermodynamics rigorously, I don't have to just say, oh, it's at constant temperature and pressure, right? I would have to say, well, it's also at constant potential or it's at constant charge. Okay, I would have to specify 3 variables. Okay, so much of this lecture is going to be about equilibrium. And it's both mathematically but also conceptually a little bit involved, and I'm sure you will figure out the math, but I really want you to pay attention to the conceptual questions. So what have we learned about equilibrium so far? That if we have an isolated system, and now we know what that means, right? Isolated means that its extensive variables are constant. So there is no way to put any energy in or out of the system. Right? For example, its volume is constant, so I cannot do mechanical work. It's closed, so I cannot do chemical work. It's insulated, so I cannot do heat transfer. What I know for a system like that, right? For a system like that, the second law tells me that the entropy has to go up. So the system can only evolve in a direction that the entropy goes up, which means that if I were to plot the entropy over some time, right, it would have to do this and be at some maximum, and anything beyond that would be a virtual trajectory that couldn't happen, and here the system would stop, right? Because the entropy is maximal, and so stop means this would be equilibrium, because by definition the system would stop evolving there. Now let's say we have a simple system with only PDV work. So what I have also told you on the left board here is that ds is equal to du over t plus p over t dv. So, you know, when I study thermodynamics, and I've taken way too many courses in thermodynamics, I got to tell you that this puzzled me for a long time. So, because we're at constant extensive variables. So entropy changes with them. So when I say you maximize the entropy, what am I maximizing over? Because all the variables that claim to modify the entropy, right, U and V, they're constant. So what am I maximizing over? This is kind of an important concept because there's a lot of confusion about it. And then, you know, what's the point of that equation that I wrote down there in pink? There isn't a whole lot to maximize there, right? Does anybody give it a shot? Like when somebody says I maximize the entropy, I think I just proved that it's constant. So what we maximize over is the internal degrees of freedom. This du, this u, and this v, these are the boundary conditions on the system. This is the total imposed energy and the total imposed volume. But I may have internal degrees of freedom. And I'm going to give you examples of that so it'll become a little clearer. There may be internal degrees of freedom that are consistent with those boundary conditions. For example, I am at constant energy, but how do I rearrange that energy in the system, right? Let's say I have a complicated system inside. How do I rearrange that energy? That's a degree of freedom. How do I arrange the volume, right? Let's say I have different masses, different species. How do I arrange the volume? Those are the internal degrees of freedom. So what you maximize over the set of thermodynamic states that is consistent with the external constraints. So an example is the distribution of the extensive quantities in the system. So if you wanted to write the maximization equation in a maybe mathematically somewhat more sensible way, you would write it as the entropy at a given set of extensive variables, right? The constraints is the maximum over any internal variable of this function su xi and the internal variables. It's what's in mathematics called a projection or an integrating out of degrees of freedom. You're removing the internal variables by maximizing the entropy over them. Okay? And I'm going to give you some examples of that to clarify that later. So then when I write down the pink equation, when I write down this equation, what does it tell me? What this really tells me is how the equilibrated entropy varies with the boundary conditions, right? So I minimize S at one volume and U, and I minimize it at another volume and U, and it tells me how this function, this guy, which is already maximized, which is already optimized, how that varies with the boundary conditions. Okay? So there is sort of a shortcut that I know students and teachers make in thermodynamics, which leads to the right answer, but for the wrong reason. People say, like, oh, how do I know S is maximal? Well, U is constant and V is constant, so this is 0, so this is 0, so S must be a maximal. That gives you the correct conclusion, but for completely the wrong reason, right? There is no maximization in here in this equation. The maximization is already implied. You're not maximizing this differential or anything, right? Okay? So I'm going to give you, if you're sort of in doubt, let me give you a series of examples and then we'll generalize. So I'm going to do first thermal equilibrium and then mechanical equilibrium. And you'll get so good at this that you can do any equilibrium afterwards. Okay, so I'm going to take an isolated system. But I'm going to partition it in two parts. I'll call them Roman numeral 1 and Roman numeral 2. The partition is rigid, so it cannot move, but it can let energy through. So let's say it's a heat conductor, right? So it can transfer energy from left to right. And the other way, of course. You should always, like, when I say the partition is rigid, it doesn't move, that should right away in your brain click, volume cannot redistribute, right? If the partition is rigid, basically what I've said is the volume of system 1 cannot change, the volume of system 2 cannot change. So they cannot do work on each other. Okay. So what does equilibrium give here? So the total entropy has to be maximal. So I'm going to calculate the differential for the entropy of the system and then figure out ways that I can make it go up. If I can make it go up, then it wasn't maximal, right? So the entropy of the total system is the entropy of subsystem 1 plus the entropy of subsystem 2. If we assume that the subsystems are in equilibrium themselves, then this is equal to, then the only variation of S1 that can arrive is by energy transfer, internal energy transfer. So this is du1 over T1 plus du2 over T2. But now the total energy of the system is conserved, so du2 is minus du1. Right? That's how I impose my boundary condition. So what I get is that this is equal to du1 times 1 over T1 minus 1 over T2. Okay? And now you see that in most cases, I am not in equilibrium. So if T1 were to be greater than T2, right, then this here is smaller than that. So I have a negative sign on the temperature term. So in that case, I would make du1 negative, and that would cause a positive ds. So the entropy would go up. So I cannot be in equilibrium. By the same argument, if T1 were to be less than T2, then I would make du1 positive, and then that would make the entropy go up. So what you see is that unless the temperatures are equal, there is always an internal variation of the system that I can do that makes the entropy go up. So the only equilibrium that I can find, the place where I cannot increase the entropy anymore, is when T1 is equal to T2. Right? Because if I have this condition on the temperature, there is no way I can make the entropy increase. Therefore, I have to be in equilibrium. So it's pretty easy to see here that I could have just called system 1 the environment and system 2 my real system, and taken the total as the universe, right? The universe I can consider it closed. So if 1 is the environment, 2 is my real system, I will find in general that if I have walls that let energy or heat through, that temperature of the system will have to equal temperature of the environment, right? Something we know intuitively. It's a generalization here. So I could have done this with 3 subsystems, right? You know, I could have made as many as you want. I could call them 1, 2, 3. And looked at variations between them. I should try that sometime, right? And what would you find? You would find that the only way that you cannot increase the entropy anymore is if the temperatures of all the subsystems are equal. And look at that by analyzing the equations, right? Any time that there's a system where the temperature is different, a subsystem, I can transfer entropy in or out of there to make the entropy go up, right? So the general conclusion is that if internal energy can flow inside a system, then the temperature has to be homogeneous. So the state of maximum entropy is the state with homogeneous temperature. With homogeneous, I mean that it's the same everywhere in the system, right? I was going to reach for my coffee, but then you lose the board, right? Let's see if I can do this. No. I'll come back quickly. Okay, let's do one more, and then I think you'll see the generalization. So let's do mechanical plus thermal equilibrium. So again, I'm going to take a system that's fully isolated from the environment. And now I'm going to have a dividing wall between the two subsystems, but now the wall can move. So it's diathermal, so it lets internal energy through, but it can also move. That means I can change internal energy, but I can also change volume between the two systems, right? Because that's what the moving of the wall means, right? If I move the wall to the right, I make the volume of system 1 bigger and the volume of system 2 smaller. Okay. So we're going to do the same thing to derive the equilibrium condition. ds is ds1 plus ds2, which, since I know that ds is du over t plus p over t dv. So, and conservation, the fact that the total extensive variables have to be constant means that du1 is minus du2 and dv1 is minus dv2, right? Because the total volume of the box is closed. So I'm going to go a little faster now, right? So you plug these both in and you get that ds is equal to 1 over t1 minus 1 over t2 times du1 plus p1 over t1 minus p2 over t2 times dv1. That's the total entropy. Entropy change, sorry. And what you see now is that I have two independent variations. So both of their prefactors will have to be 0, right? To make sure I can not find a way to increase the entropy. So that means that, again, we find that because the wall is diathermal, the temperature has to be homogeneous. So T1 is equal to T2. And then we find here that P1 is equal to P2. So what you see, right, is that for every independent internal variation, you get an equilibrium condition, right? So I can flow the internal energy, so I get a condition on the temperature. I can flow the volume, so I get a relation on the pressure. These internal variables that we optimize over do not have to be continuous variables. They can be discrete variables too. So I'm not sure discrete is the right word, but I haven't found a better one. So again, let's say I have an isolated system at constant extensive variables, so u, v, and now I'm also going to take mass numbers. So n is the number of moles, say, of species I. Let's say that, let's just for now take species I as just an element, so there's only one. Let's say I can be in two phases, right? Let's say it can take on two different crystal structures. So, you know, maybe, you know, I can be in structure alpha. I should really say phase alpha to be correct. Or I can be in phase beta. So I could treat that as a discrete variable. So I could not write the entropy of the alpha subsystem. That's the part of I that's in phase alpha. That would be U V and Ni in alpha. Although in general, I'll leave it like that, sorry. And then S beta would be U, V, the amount of Ni in beta. And what equilibrium tells us that the phase with the highest entropy will win. Again, this is a bit of a strange equilibrium condition, right? Because we are minimizing at constant u and v. Okay? So in this case, we would minimize the entropy over the degree of freedom, which is this one. Right? We would minimize over how much of each of the species is in phase alpha versus in phase beta. Okay? That's the internal degree of freedom here. What you see in general is that when I let an extensive variable redistribute in the system, so when I let it flow in the system, when it has no restrictions in the system, then basically we find a condition on its conjugate, right? But it's conjugate in the entropy notation. Here I let the volume flow, so I find a constraint on the pressure. So what would happen if I let mass flow? So I have a system and I let mass redistribute. You can already write this out without even understanding what chemical potentials are, but you would have to have some intensive quantity, homogeneous, that's the conjugate of the amount of stuff, the mass. So there has to be some variable that's du dni, right? At constant entropy and all the other xj's that are not equal to ni, right? And that we will later see is the chemical potential of I. And so even if you don't know what these things mean, right? If you think of it in pure mathematical terms, if an extensive variable can flow, that means it can redistribute entropy in the system, then its conjugate has to be homogeneous. And in this case, the conjugate will be the chemical potential. There's a cute example that I think, I'm not sure if it's still in the problem set, but since we cut out a bit of the problem, but it used to be one of my favorite exam questions, so it's definitely in old exams because it's so elegant. So what if the flow of two extensive variables is coupled? So coupled internal extensive flow. So that the variation of, I'll call it 1, sorry, of extensive quantity 1 in any location is 8 times the variation of extensive quantity 2. So they are coupled. If I change what I do to variable 1, it couples to what I do to variable 2. This is not just a mathematical problem. This is actually quite real. For example, if I use membranes that can only transport ions, then every time I move mass, right, I use the number of mole of some ions, I'm also moving charge because I can only move mass as charged mass. So that's an example, right? There's examples like this in magnetism. If I move in a ferromagnetic system ions that carry spin, then I'm moving magnetic moment with the ion, and so I'm coupling two work terms together, basically. So what I'm going to let you prove is that now the equilibrium condition is not just that the conjugate of x1 is homogeneous and the conjugate of x2 is homogeneous, it's actually a coupled condition. So equilibrium now, which you should try to derive, is that y1 plus 1 over a y2 in subsystem 1 is equal to y1 plus 1 over a y2 in subsystem 2. So basically, what is homogeneous now is this linear combination of intensive variables. So Let's run a little ahead, right, to have fun, because I know this is pretty abstract. If X is number of moles of something, X1, and X2 is charge, then what am I coupling? I'm coupling their conjugates. The conjugate of mass is chemical potential, and the conjugate of charge is electrical potential. So what I've just re-derived is essentially Nernst equilibrium, right? That if you have a system in which mass travels as ions, I couple chemical potential to electrical potential. And neither of the two is constant. It's their linear combination that's constant. So if I set up a system with, if system 1 has a very different chemical potential for species 1 than system 2, then I will also have a different electrical potential. Okay. Don't worry too much about this. If you are getting lost, we will derive Nernst equilibrium later. But you can see that this falls very elegantly out of equilibrium conditions, right? But try to do that derivation yourself. So I want to make one more generalization, and that's to continuous variables, so densities rather than fixed quantities. So you can apply this completely to non-homogeneous systems. So you can generalize this to continuum distributions. So now, rather than determining extensive quantities, I'm going to define the extensive densities. So I'm going to define an entropy density as a function of position. So now I'm describing my system with some vector r. And at each position in space, I will have, say, an entropy density. You know, I may also have an internal energy density, you know, volume, whatever, right? Whatever extensive quantities are in play. So I have a bunch of densities there. Maybe I have V. Okay, so now these are, they're still extensive in the sense that they play the role of extensive variables in thermodynamics, but they are normalized. So in a system like this, where I have continuous variables for the extensive quantity, but the system as a whole is isolated, right? So I have a density of internal energy, etc., of entropy, internal energy, etc. What is the equilibrium condition? Well, it's the same, right? Remember that thermodynamics couldn't give a hoot about what's going on inside, right? Thermodynamics just wants to maximize the total entropy, which is now the integral of the entropy density over R over the domain. And that would be under constraints under conditions that the integrals of the other extensive quantities are fixed. So maybe I should write in general, let me write in general xi. This is the density of large X. It's not a composition, in case you get confused, right? This is the density of large X under the condition that xi r dr is constant. So this is xi total, and this has to be constant. So this is your general equilibrium condition for a system in which things are not homogeneous, right? Maybe I have like, I don't know, very different regions of material around. So that I have to sort of, maybe I have inhomogeneous concentration or something like that, right? So I can't sort of just call discrete subsystems 1 and 2. Any system that would be inhomogeneous, you just apply maximization of the entropy integral under the conditions that the extensive quantities are constant. Now you want to know something really cool. What is kinetics? We are missing one derivative here to explain all of kinetics. What's the derivative? Time, thank you. Kinetics is the time derivative of this. So kinetics is nothing but maximizing the entropy production, right? Almost all kinetic equations can be derived from the idea that at any given time, you maximize entropy production. So kinetics is essentially the fastest way to go to your equilibrium, right? Because your equilibrium is where this entropy is maximal. So kinetics is just going to maximize the entropy production. And, you know, you can get the diffusion equations out of this. You can get the heat transport equations out of this. You can get pretty much anything out of this, okay? Any sort of linear form of kinetics will drop, which is like 99% of them will drop straight out of them. But of course, if you think about it, right, to calculate what this time derivative is, I need to know, because S is influenced by these fields, right? So I need to know what the time derivative of these fields can be, right? And that's essentially where all the kinetic constants come in, right? You know, heat conductivity and diffusion constants, etc. Right? But the reason I'm telling you is that there's often a sort of orthogonalization that people imagine between thermodynamics and kinetics, right? Oh, thermodynamics is about equilibrium and kinetics is not about equilibrium, but it's actually not true, right? Kinetics is really, you know, desperately seeking local equilibrium, right? That's really what it is. It's going to local equilibrium as fast as possible. So these sciences are not nearly as orthogonal as people make them appear, okay? Okay. Let me briefly switch to screen sharing. Okay. Only tell me if you don't see this, but I think you do. We have so far used what's called the entropy maximum principle, right? Which says that you find equilibrium by finding the unconstrained internal variables that maximize the entropy. Right? There's a corollary to that, which is what's called the energy minimum principle, which basically says that you can also find energy by minimizing U under constant entropy. This is the simple paraphrasing of it, right? So in the first case, we maximize entropy under constant energy and the extensive work variables. Now we're going to minimize internal energy under constant entropy and the extensive work variables. And this is sort of described in detail in Callan on page 132, at least in my version. But I'm going to give you sort of a quick and dirty derivation of it. Okay. So I'm going to do this by prove by negation. So basically we want to argue that maximum S implies minimum U under the right boundary conditions and blah, 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 right? This says implies here. So I'm going to prove this by proving that the negation is impossible, right? So I'm going to take a state for which S is maximal at a given U, and I'll call that value U1. And I'm going to assume that this statement here is not true. So that means that U would not be minimal. U1 would not be the minimum at the value of S. So I'm going to prove to you that that's not possible. So under constant entropy, I would find equilibrium for a given value of U1. If that value is not minimal, then I can extract U, right? Because it's not minimal, so I can go lower. So I extract U by doing work. Which means I end up in a state that's because work doesn't change the entropy, so I'm at S. I'm at S and I'm at a value of U1 minus delta U. And somewhere out here is sitting work, which is equal to delta U in magnitude, because I've extracted work, so I have work somewhere in the environment. So I can always convert that work to heat. So I'm going to convert that work to heat by dissipating it, and I'm going to add it to the system. So I add that heat. So what do I have? Energy came back in, so I'm at U1, but I'm at a state that's higher entropy. So S here is the S prime is the original S plus some delta S, which I could calculate from Q over T. But the fact is that it's positive. So what that means is that I just made a state that has higher entropy than this one with the same internal energy, right? But that was my beginning statement, right? So basically what I conjecture here is not possible. So I basically proven that under all conditions, maximum entropy implies minimal energy. And if you want to read more about this, this is sort of described in some gory detail in Callan. So what I want to do for the rest of the class is define equilibrium under more general conditions. So we have so far only derived equilibrium conditions under constant, no exchange of energy with the environment, no heat, no work. So that's usually not what happens, right? Normally we have systems that are open to the environment, or systems that do PV work, or systems that can exchange heat with the environment. So I'm first going to derive equilibrium under general conditions, and they will be remarkably general, And then what we'll do is we'll systematically make them less general. We'll apply them to specific conditions. But I first want to give you the most general, which I've never actually seen in a book. I got it from some old lecture notes of Desfontaine, but I'm not even sure it's actually in his book. This is equilibrium under general conditions. So we're going to define a system in an environment. So I have the system, I'm going to embed it in my environment. And the sum total of the two, I'll consider closed, right? So the sum total of the two is closed, is isolated. I know that I'm kind of often a little ambiguous. Isolated is already closed too, right? But so it's adiabatic, it has constant volume, blah, 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 right? So the way I'm going to find the equilibrium condition for the system is by treating it as an internal equilibrium of the universe, right? System plus environment is the universe. So if I can internally equilibrate that, I have the equilibrium of the system. So equilibrium of the system is the same as internal equilibrium of the universe. I'm going to make the environment large enough that its intensive variables are constant, right? Which I can always do, right? I can make the environment infinitely long. So for the environment, I'm going to assume constant intensive variables. So things like T, P, etc., right? And now one more thing. Parameters of the environment, I'm going to write with a star. So if I talk about T star, there'll be T of the environment, and no star. So star means variables of the environment. No star is system variables. Okay? And then two more equations that I could write down. Of course, since the system as a whole is closed, I can apply the first law. So delta U star plus delta U has to be 0. Right? Energy conservation in the universe. And then, because the system as a whole is closed, delta S star plus delta S has to be positive, right? So the entropy of the total thing, the entropy change of the total thing has to be positive. Okay, with that, I can now derive full equilibrium. Let me hang out a bit here, but I think you got it copied probably by now. Wheel of Fortune. Okay. So if I write the combined first, second law for the environment, I get delta U star. I don't know why I wrote finite differences here. I could just as well do this with differentials. Somehow I did this in my notes, but it doesn't really matter. So it's T delta S star plus sum I yi star delta xi star. Okay. So I use now the fact that the extensive variables of the universe are conserved. So that means that this here equals minus delta U. I'm not going to do anything yet with delta S star, but this becomes this becomes minus some I yi star delta xi. And now I use the second law. I'm just going to multiply this here by T star, which is a positive quantity. Maybe I'll bring it over so you can. So T star delta S star is greater than or equal to minus T star delta S. So I can put that in here now. So what I get, I'm going to multiply by minus sign here. Now I'm going to bring this to the other side. So I get that delta U minus T star delta S minus some I yi star delta xi has to be less than or equal to 0. And let's pause for a second here, because it's kind of a remarkable equation, right? So if you've had the time to write it down, what this is an evolution law for the system, right? Because it's telling me how system variables, right? U, S, these things don't have stars on them, right? And xi, how they change in fields of the environment. Because the fields, like T and yi, right? This is the sort of applied fields that the system feels. These are from the environment. So what's kind of powerful about this equation is that for now, I haven't even assumed that the system is at the same temperature as the environment, that the system is at the same pressure, right? Yi could be the pressure of the environment. The pressure in my own system could be different. T star could be different from T. So this is a remarkably general evolution law. And what we're going to do to make our life easier is we're going to start generalizing it. Sorry, not generalizing it, make it more specific so that we can more easily apply it. But you can always go back to this because this is essentially a pure statement of the second law, right? It's basically telling us that, you know, it's telling us this here, right? That the total entropy change in the system has to be positive. I'm going to come back to this, so I'm going to leave it on the board because there's a subtlety in our derivation. But first, I want to generalize. So, I always say generalize when I mean make more specific. So, we know from what we've proven before that internal equilibrium in the universe, because the extensive variables can flow between the system and the environment, will require that the intensive variables become homogeneous. So, at some point, the system temperature will have to become equal to T star. And at some point, whatever yi the system takes will have to be equal to y star. So I'm going to now continue, assuming I got there already. So internal equilibrium of the universe at some condition requires that T star becomes T. I really should say that T becomes T star and that yi star equals yi. So, and just to make your life harder, now I switched in my notes to finite differences, which I could, right? There is nothing in my derivation that meant these had to be finite differences. They could, but so what that means is that du minus TdS minus some I yi dxi has to be negative. And you could take this again as a general evolution law for systems, because now you are only in variables of the system, right? So if you have no clue what's going on, this is always a good equation, right? Because we haven't really put any constraints on this. Okay. And if you apply this, for example, for a simple system, where we only have PDV work, then du minus TdS plus PDV has to be negative, right? There is a subtlety that I just want to alert you to. It's not something I did wrong, but it's something I swept under the rug because it's a bit of a mess in thermo. I've assumed that these are conserved all, right? Because I went from, here's my subtlety, right? See here, this term is positive, and here it goes negative because I basically said here that delta xi star is equal to minus delta xi, right? Which I didn't write on the board before, right? I just said energy is conserved. Now I'm making a stronger statement that all the extensive variables are conserved in the universe, right? What do you think about that? Do you think it's true? It's a pretty subtle question because, okay, we believe it for energy, right? That's the first law. You believe it for mass, right? Except for relativity, and thermodynamics is not supposed to deal with relativity, right? You believe it for mass, right? Atoms don't disappear, right? Unless I do nuclear things. What about some other variables? Like, what about magnetic moment? Do you think magnetic moment is a conserved quantity? It's actually not. And I'll tell you where the subtlety comes from. So, because I don't want to make your life miserable, nor mine, if you really want to do thermodynamics rigorously, you should not treat electrical work and magnetic work as independent of each other. And the reason is that they are coupled through the Maxwell equations, right? Basically, right, these things people wear on their t-shirt in Berkeley, the Maxwell equations, right? Or in any university. They tell you that like the time derivative of one is something about the other one, right? That's basically what the Maxwell equations tell you, right? So you clearly can't just change one without the other, without doing something to the other. And what we know, right, if you've taken like, I don't know, much higher level electromagnetism than I ever took, there is actually a conserved quantity in electromagnetism, and it's essentially the vector, what they call the vector potential. It's some combination of magnetic and electric fields. And that's the conserved quantity. So we kind of cheated here because I didn't want to like annoy you nor myself and do electromagnetism. But magnetization is not really conserved by itself. So the reason we're okay with this is we get the right answer, trust me, but we kind of fudged a little bit here in the derivation, okay? This is true for most extensive quantities, and it's true if you do things like electromagnetism correctly in thermodynamics, but in our kind of slightly abbreviated version, it's not technically true. But having said that, from now on, you are allowed not to worry about it anymore, and the equilibrium conditions we derive will be the right one. If you really want to learn about it, be my guest, okay? And you can come and tell me about it. Okay. Let's see how good this is, this equilibrium condition. You sort of work backward and see if this kind of tells us what we already knew, right? So let me apply it to some specific conditions, just to see if it jives with our intuition. So hopefully, if I go back to an isolated system, I'll find the right answer. So if I do an isolated system, right, then du is 0, dv is 0, right? So what I'm finding is that minus TdS is negative, so I find that ds is positive, okay? That's kind of what we figured out, right? So we're finding back basically a statement of the second law if we have an isolated system. Okay, what if I have what I'll call a mechanical system? So this is a system where there's no entropy generation. Also dV is equal to 0. So if I set these two to 0, then what I prove is that du is negative. And that's kind of what we know, right? In mechanical systems, you go down to the lowest energy state. If I have a system that's isentropic and isobaric, it's kind of a weird system, but right, so constant pressure, but constant entropy. So then I find that du plus pdv is negative. And if I'm at constant pressure, I can rewrite this as du plus the differential of u plus pv is negative. And the thing in the differential is the enthalpy. So in this case, I find that the enthalpy decreases. And if I go isothermal, so constant temperature, and isochoric means constant volume. So if I'm isothermal, I can get TdS exchange, but if I'm isochoric, I have no mechanical work. So I now have that du minus TdS is negative. And because T is constant, I can write it as du minus d of u minus Ts. And this combination, just like enthalpy, gets defined as Helmholtz free energy. It gets a name. Come on, camera, go down. Come on, baby. Let's try this again. There we go. Yeah. Okay. F is u minus Ts. This is the Helmholtz free energy. Come on. Did you get it? And since you've all had undergraduate thermal, you know where this is heading, right? If I do isothermal, isobaric, so constant temperature, constant pressure, then I get du minus TdS plus PdV is negative. So that is du minus Ts plus PV is negative. And this combination is defined as G, the Gibbs free energy. So this is I'll come back to this quite a lot more in the next lecture, how you should sort of interpret these different functions. Okay. So what I've sort of derived here is for a simple system, a system that only does PDV work, that if you apply different boundary conditions, you look at different potentials that are optimized, right? Either entropy goes up or energy goes down or enthalpy goes down or Helmholtz free energy goes down or Gibbs free energy goes down, right? So I've looked at different potentials. So why do we use different potentials, right? Why is it not just the energy that goes down, or why is it not just the entropy that goes up? So I want to show you sort of an example of a sort of trivial system, hopefully to explain this. So this is sort of a side example to help you with the interpretation of the potentials. So let's say I have a sort of ceiling here, and I have a ball suspended from it to a spring. And this ball is in a gravitational field. And I'm going to take the ball as the system. So this is my system definition. So the energy of the system is minus mgx. And I have to define x, right? So I'm going to take x in this direction, downward. And I'm going to set the 0 here wherever the equilibrium length of the spring is, right? The 0 force length of the spring. So you could call that the x0 of the spring. Okay. And the spring here has some spring constant k, right? So it's obvious to you that to find equilibrium, I am not minimizing the energy of the system here, right? Because what's the energy of the system? Well, it's the ball as far down as I can get it, right? Because this is the energy of the system. So I want to make x as large as possible. So energy of the system minimized means ball down through the ground here. So obviously that's wrong, and why? Because my system is coupled to the environment, in this case to the spring. Just like a thermodynamic system is coupled to the environment through its energy flows with the environment. So let's think of this now as a thermodynamic system, not a mechanical system, and let's see if we get the right equilibrium. So what is the force? So there is a force on the system, right? It's external to the system because it comes from the spring. So I'm going to call that F star. That's by analogy to my previous derivation. And F star is pointing upward, so it's minus kx, right? And that's because I've defined the 0 of x, just to keep my life simple, as where the rest length of the spring is, right? What the 0 force length of the spring is. Okay. So let's now let's do this purely thermodynamically. So I'm going to write down the generalized equilibrium condition, which I had on this board here that I erased, is that du of the system minus T star ds minus yi star dxi is less than or equal to 0. I have no heat flow, so this goes. What is yi star? Right? This is the conjugate force on my system coming from the environment. So that's my spring force, right? So this here is F star. So let me write out now what is U system. U system is minus mg dx. So what's the variable here is where the ball is, right? That's x. The spring constant, I do minus y, and the force is minus kx. So this is plus kx. And the extensive displacement is simply dx here. So thermodynamics tells us that this has to be negative. So I can cancel the dx's. So what have I just proven? I have just proven that kx minus mg. Okay, I should have kept the dx. Sorry for a second, because I don't know. I did something wrong because I don't know if dx is positive or negative, right? So I can't really divide it away. Sorry about that, because I have an inequality sign here. So I have proven this statement, which, if you think about it, makes sense, right? This is the spring force. This is the gravity force. If the spring force is larger than the gravity force, right, then dx is negative, right? The ball goes up. If it's the other way, dx is positive, the ball goes down. So what's equilibrium? Equilibrium is when this potential here, this is now my thermodynamic potential, kx minus mg. So equilibrium is when kx is equal to mg. So, and obviously you knew that, right? You know how to calculate mechanical equilibrium, no fools, but what you see is that your concept of mechanical equilibrium is completely consistent with the evolution law of thermodynamics. If you just did mechanics, of course, you don't need thermodynamics because we've kind of removed thermodynamics here, right? By getting rid of the change in entropy. But what I told you in lecture 1, that thermodynamics will incorporate all these fields together on one consistent footing is true here, right? So I derived a bunch of thermodynamic potentials, and when I reduce them back to mechanics, I get exactly the mechanical equations that I was expecting. You can also now see why you have thermodynamic potentials, right? You have thermodynamic potentials because you shouldn't just minimize the energy of the system, right? You have to minimize something that incorporates interaction with the environment. So you can kind of see that in the potentials if you pay attention, right? If you take a simple system and you take the enthalpy, so if you remember, right, the enthalpy is the function that I minimize when I have just PDV work with the environment. If you remember this here, right? So I'm isentropic, so I'm not doing heat exchange, but I have PDV work. So in some sense, it is the mechanical function that I've shown here. So what does this potential mean? It's basically telling me, well, I minimize my internal energy, that's part of it, but I also have this PV term, which is my potential energy in the environment. Because if I have a large volume, then there's a lot of potential for the environment to do work on me to deliver energy, right? If I have a large volume, the environment can compress me a lot, and by that, doing that, deliver work on me. So PV is the mechanical potential energy of your system in the environment. So what you're minimizing is the internal energy plus your potential energy in the environment. So it gets more complicated when you look at the Helmholtz free energy. The Helmholtz free energy, right, takes care of the thermal piece. So now there's no volume work. But if I have large entropy, that means that I've already received a lot of heat from the environment, right? So I don't have a lot of potential anymore to receive energy as heat from the environment. That's why this is minus Ts, right? High entropy counts against you as potential energy. If I have low entropy, then the environment can transfer a lot of energy to me. So minus Ts is your thermal potential energy in the environment. And then, of course, Gibbs just puts the two together, right? I have my mechanical potential energy and I have my thermal potential energy in the environment. And that's why you minimize those, right? So I know I'm over time, so I'm going to end here, but what you should remember, and we'll come back to this on Wednesday, that obviously you don't minimize the energy of a system, right? Because it's constantly interacting with the environment, so you have to come up with different functions or different potentials that you minimize, just like in this trivial mechanical example here. And that's what the thermodynamic potentials are. What we're going to show you, I think on Wednesday or the lecture after, is how you do this more generally, right? These are sort of trivial examples. I only have PDV work. You know, I'm either just under constant pressure or temperature or two. So how can you develop potentials for general boundary conditions? What if I have a thin film that I do epitaxially, right? What's my boundary condition? What's the right potential? What if I have a system under constant voltage? Okay, so I'm going to end here because I'm already 2 minutes over time. Good seeing you all again. Glad you're still here. And I'll see you on Wednesday. Take care. Bye.
Can I ask a quick question?
Yeah, quick.
So when we had du minus TdS minus y dx,
yeah,
is less or equal to 0, and then we said for a simple system where there's only PV work, why does the sign change to plus? So I think it was du minus TdS minus y dx.
Because, so for, maybe this answers, I'm not sure I totally got the question, but let me try. Because yi is minus p.
Oh.
Yi is not plus p, it's minus p.
Okay.
Is that clarified?
Yeah,
okay.
Yeah, I got that. Okay, thank you.
Any other questions? We'll still be office. Yeah, go ahead.
I was wondering, how did we get rid of the minus TdS for the spring system?
Here.
Yeah.
Okay. Because I'm treating it as a purely, this is a choice I made, I'm treating it as a purely mechanical system that is not doing any thermal exchanges with the environment, right?
So
I'm assuming there is no heat flow here with the environment.
Okay. Thank you.
Yeah, you're welcome. Any other questions? Okay. Enjoy a new week. See you on Wednesday. Bye.